So we've talked about polynomial and rational functions. We've talked about power functions, rational exponents. I guess those are all called algebraic functions. These are called transcendental functions. I never called them that.
Transcendent.
Whatever. They're still algebraic in my eyes. But how are they different? Like when you compare x squared. So x squared is a power function. And of course, that's an exponential function. How are they similar? They both have exponents. I mean, I think it's pretty obvious, right? But how are they different? Yeah, the base is x, or y equals x squared. But the exponent is x, or the input, right? Or the input's the exponent, put it that way. Okay, so that's what's happening with that one. What's the definition of exponential? What's the definition of an exponential function? Right there. A represents the initial value, B represents your base. B could also be thought as the exponential, the growth factor or the decay factor. Why do I use those words, growth or decay? Growth obviously means you're growing, going up. Decay means you're going down. What value do you think B has to hold to be growth for this type of function? Yeah, greater than 1. If it's exactly 1, then it's just linear.
Oh,
To be decay, what do you think B has to be?
less than 1.
More specifically,
Negative.
between 0 and 1, non-inclusive. If it's negative, it's gonna be weird. Why would it be weird to be negative for B? That's one reason. Also, you wouldn't be able to use a fraction, like 1/2. You can do 1/3, but you can't do a fraction with the even exponent. Sorry, with an even denominator for the exponent. So that's because if you have all these undefined points, so that's just weird. So our B values are going to be positive, more specifically between 0 and 1 for decay, non-inclusive, or greater than 1, non-inclusive for growth. If it's exactly 0, then y equals 0, exactly 1, y equals 1, or y equals a. So we got to be mindful about that. Okay. So looking at these here, we're going to determine whether it's an exponential function, identify the initial value and the base. So which ones are exponential? That one, that one, that one, not these two. That's just going to be a constant. Yeah, see, I threw you for a loop, right? 6 to the pi power is just a number. That's just a constant. That's a power function. Clearly, my initial value is going to be 1, and my base is going to be 3. Here, my initial value is -2. My base, 1.5. The base of the power. Correct. Correct. Initial value here is 7. Base is going to be 2. So this should all be very straightforward stuff, right? We're okay with that? Okay. Can I move forward? Okay. For example 2. If I plug in 0, I should get 1. Then I should get 1/3. That's, of course, just root 3. Well, that's a fun one. 3 to -3 halves. That's 1 over root 27, I think. H of 0 is -3. That's me -6. That's -3 over root 2. And that's -3 times root 8, I think. Yeah, I'm kind of skipping some steps here.
So what am I raising today? 3/2 power. 1/2, right? What's the negative exponent to? So it becomes 2 plus 2 cubed. And then square root of 8. Does that make sense? Then I clean it up by making that 2 root 2, right? I pull the 4 out, right? From 2 root 2. So yeah, that's kind of a nice one actually.
Could I have simplified g of -3/2? I probably could have, right? How could I have cleaned that up a little more? Yeah, and since sometimes I don't really care to be honest, but some tutors don't like radicals in the bottom. So you get root 3 over 9, if you wanted to write it that way. All right. Cool. Okay, moving right along. Graphs of exponential functions. I know, very exciting stuff. We talked about this. B is a growth factor. Technically, A could be negative. It still could be considered a growth function, just flipped, but that's fine. We'll keep A positive. We don't need a graph in the calculator. You kind of know what's going to happen, right? Like, that's your first graph, right? Oh, your next graph. And next. Yeah, it gets kind of hard to draw after a while.
Can't y not be negative?
It's not negative. It's
Sorry.
going close to the x-axis. No, x can be negative.
I was mixing up x and y. My bad.
No worries. It's all good. You have that. So what do they have in common? 0, 1. Their characteristics are all the same. They're all real numbers. Continuity everywhere. Symmetry none.
What is continuity?
Where it's continuous. The interval where it's continuous, but it's continuous everywhere. The range is from 0 to infinity. It's always increasing. Asymptotes, y equals 0. By the way, some of you guys did get asymptotes kind of mixed up on our what was it, this class? No, sorry, that's my algebra 2 class, not you guys. You guys are better than that. All right, never mind. You guys good. Extremity is none. Because there's never a low point, right?
do I truly know what the lowest point is? No. It gets awfully close to 0, but never exactly.
The bound is kind of a weird one. I never really talked about this. We say it's bounded below. It means it doesn't go down forever.
See, does it go up forever? Is there a ceiling to this graph? No. Is there a basement? Yeah, there's a floor or a basement. Does it hit it exactly? No. But it doesn't go down forever.
So let me define boundness for you guys.
How does it not go? Doesn't it go down forever? Because it's getting like a little bit smaller.
It's not going towards infinity. That's what boundness is about.
Oh,
So like
okay.
So to be bounded below means y never approaches negative infinity. Think, Olivia. Bounded above means y never approaches positive infinity. I'll look at your notes too, though. Yeah, so that's what that means. I don't care about, because it's not really something that's mentioned in calculus, so I don't really care about that definition, but just so we at least have that discussion. And then end behavior, the limit as x approaches negative infinity and the limit negative infinity f of x and
Okay,
no, my ands suck. No, you're good. All this is that a semicolon? Good. Okay, if you're going further to the left for x, what's y doing? What's y approaching? How about if I'm going further to the right? What's y approaching? Right, correct. Okay. So those are the properties of a growth function. So again, domain's all real. There's no need to restrict x. X can be whatever you want, just an exponent. It's continuous ever. There's no breaks in the graph. The range, obviously, it's y gets close to 0 because you're multiplying 2 a bunch of times. It's never going to be 0 because then you need a 0 to multiply to. It's always increasing. Just look at it's always going up as x goes up, y goes up. Bounded below because it doesn't approach negative infinity. To be bounded above would have to be y never approaching positive infinity. That's just my OCD kicking in. I don't like that. There we go. Okay. End behavior, you know what that means? Asymptote y equals 0 because that's an end behavior asymptote. There's no external high points, low points. To be at an extrema, you need to switch from increase to decrease or vice versa. We don't see that at all. So that doesn't happen. So we're comfortable with how that's happening. What's going on with exponential growth? Okay. Now decay is the opposite. Well, not the opposite, but b is less than 1. Technically, b can't be negative. So I don't like that. It just says that it should really be 0 is less than b, which is less than 1. And they're going to look like this.
Why can't B be negative?
If b is negative, you have a couple problems. First off, you're going to have an alternation between positive and negative outputs, which won't quite follow the smoothness, if I want to call it that, of the curve. And also the fact you're going to have a bunch of discontinuities if you raise a negative base to an exponent with an even denominator. Then you're even rooting a negative number.
It would like work.
Here, I'll write again. It'd just be really weird. We just want to make sure b is not less than 0, that b is greater than 0. All right, so again, do a quick sketch. Here's 1. Here's -1. Now I'm kind of struggling drawing these here. Okay, not the greatest drawing, but it's okay. Kind of get the idea, right? And where are they? Yeah. The characteristics for exponential decay functions are the same as the characteristics of exponential growth function, except for what? It's decreasing. Always. So we don't have to repeat that table again. It's still bounded below, no extrema. What? Oh, true. Yeah, you reverse. So in this case, the limit as x approaches negative infinity is positive infinity. And the limit as x approaches is 0. Okay, cool. Okay, transformations. Let me just take a quick scan of, okay, E. Let me look at the homework too. All right, we'll see how far we can get. There's a lot here, I know. Maybe we won't do all the graphs. I think you'll get the idea after a while. Yeah, maybe we can skip B and do A and C instead. All right, here we go. So I would start with the parent function. And just plug in like 3 values of x. Yeah, that seems fine. All right. The cloud method just means change x and y. That's what all it really means. So you change x and y. So how are you going to change x? What do you think?
Multiply by 2,
Nope.
divide by
Divide by 2. Yes. How are you going to change y?
5, yeah.
Correct. Because that's a transformation that it sees. Because the x is always the opposite. The y is what you actually see. So when I make a new table, that's called the cloud method. I think because you draw a cloud around the numbers, but whatever. 0, 1/2, and -1/2. I'm not sure what's called that. Actually, I do know. Actually, I think you do draw a cloud and show that you're changing. But whatever, you get the point. And then 2, 4, and 4/3, I think. And your asymptote's going to change too. Where's your asymptote going to be?
What?
Yeah, and you think numerically, right? 3 to 2x, the lowest that 3 to 2x could hold, or the closest 3 to 2x can get to as a minimum is 0. And you're adding 1 to that. So it's the function itself, the output will be awfully close to 1, but not exactly. So 0, 2, 1/2, 4. -1/2, 4/3. There you go.
What's the reason you divide the x by 2?
That's because in order to guarantee the same output as 3 to the x. So like for example, if I plug in 1, I get 3. What do I have to what do I have to plug in for x to guarantee the same output? Half.
Half of it, yeah.
That's why. So it gets compressed.
Okay.
Because if you kept the output's the same, but you wanted the same impact, you have to reduce x by half. That's why. Or take half of it. That's why it seems to be counterintuitive. Domain's easy. That's all real. Range is easy. Non-inclusive, y to infinity. Okay. All right, we're good? All right. Next up, you do that.
Why don't you start by simplifying it and making it equal 4 to the x minus 2?
Because I didn't think of that.
It's a good move.
Thanks. It's a good move, actually. Okay, I think you guys get the point, right? Yeah, let's not worry about it. We'll just move on. We'll just move on. Yeah. Let's go to E. Okay. No, I thought it was gonna be a decay, but you're right, it wasn't decay. I was like, you know what? I don't care to do it. It's the same thing. Not sure if you guys know, but E is designed by like this. It's like 2.718. Did Mr. Van talk to you where E comes from? Euler's number?
Compound continuous.
Yeah, it's called the natural. I'll explain. I'll use a calculator and show you why it works the way it does. So it's called a natural exponential function because E is considered to be the natural base of exponential functions. The letter E is the initial of the last name of Leonhard Euler, mathematician who introduced that notation. Y equals ETX has special calculus properties that simplify many calculations, which we'll talk about when we get there. If you're graphing the calculator, it's just going to look like this. 1, 2, 3. And it's roughly 2.7. I'll show you why it's 2.78 in just a moment. It is a growth function.
I know.
Oh. Oh. Yeah. It was nice to get that.
Okay. Cool. Now, why is E that number? Hold on. Nope, wrong place.
This is the same thing.
Yeah. How's that?
You're the ones in my, oh, it's like 6.006. Right.
Speed of light is obviously.
Oh, but you look like. We can do that more.
Oh, but yeah, it's just like.
Okay. So if we think about it, 1 plus. Actually, let's do this. This will be easier. I'm going to type this in over here. 1 plus 1. 1 plus 1 over x raised to the x power. Alpha trace. Now, if I plug 1 in, that makes sense, right? You're doing 1 plus 1 over 1 raised to the 1 power. If I plug 2 in, what do you think I'll get in this case? 1.5 squared. So you know what that is? Okay. If I plug in 10, okay. If I plug in 100, so I'm letting x go towards infinity, right? Using that limit notation. Okay, what do you see happening? Yeah, it's converging. It's not gonna keep going up forever. And so what this guy found is that if x gets really large, so compounding interest, for example, like compound continuously, is derived from this notion here. That's why E is involved in the formula. If I were to keep going, it doesn't really change very much. So it does converge.
It keeps getting bigger.
Right, of course. But the thinking is as x approaches infinity, it's going to be some sort of number, and we call it E. So is it?
Why did they stop it? Like it's different. Like
It's the same way the exponential decreases as you go left, that's never going below 0.
Yeah, exactly. So I mean, you just yeah, I mean, what is E exactly? We don't know that. We just know it's a limit situation. But what we do know is that if I were to plug in, we leave it in terms of E essentially. So like, the output would be in terms of E.
when you put like B in on your calculator, it gives you a value.
Yeah, I don't know what the algorithm is using for that. But I'm not sure how many digits it actually goes to, but it's an approximation essentially. I'm pretty sure it'd have to be an approximation. Note that the y-intercept is still, oh, geez. It's still 0.1. Now here, it's gonna be like this.
Mystery.
So
For that, like, couldn't you just plug in different numbers and have a different concept? Like, what makes them 1 and plus 1 over x? Yeah, it's so special.
well, no, what you're assuming is that x is going towards infinity. So as x goes towards infinity, E is going to converge
Like,
to some
why-
number.
Yeah.
Oh, why that?
2 plus 1 over x.
Oh, well, the thing is that they're countering each other, right? Because your fraction is getting smaller while your exponent's getting bigger. So
Yeah,
there's a bit of a trade-off. Is that what you're asking?
wouldn't it just be y equals 2 plus 1 over x, and it would just be a different constant? Like, why did they pick?
Oh, I don't know.
Like, is there something special about?
Oh, having 1, I see. That's a great question. I don't have an answer for you, and I do want to get some. But let's revisit that. No, it's good. It's a good question. I don't know. Yeah, but he's asking like why not do because it's still sort of the same. You still have some sort of convergence. Yeah, I mean, like, okay, I'll go really fast. If I were to go back here and change that to a 2, so that's what you're saying, right?
Yeah.
Like, what were the equation, I can't remember what it was, like one plus inversion two.
Okay, it doesn't like that. Okay. Ah, yikes. What did I just do?
You could do second, you could just turn, oh, never mind, break straight off.
Hold on. Still doesn't like it. I don't know. Maybe because maybe that's the reason why. I don't know. All right. And if you're doing 1 over e has the same properties as any other exponential decay function, the y-intercept is still 0, 1. That doesn't change. On page 4. Okay. Finding equations. So this is like exponential modeling. So let's look at both g of x and h of x. Okay, what does a represent, guys? And what's b going to be? Yeah, or more specifically called the growth slash decay factor, depending on whether it's growing or decaying. Initial value. Yeah, let me clean it up. Yeah, that wasn't really much better, but whatever. Initial value, right? So what's your initial value for g of x? And is it growing or decaying? By how much? There you go. So you don't really have to do any work. You kind of just see it. How about for h of x?
Okay.
By how much? 1 over 4. Or you do 4 to negative x. Same thing.
But you also like plug in.
You could, but you can kind of just see because the table's very detailed and orderly because x is increasing or decreasing by 1 or changes by 1. Okay. All right. So we're good. All right. All right. So example 5. Let's see here. Population San Jose in 1990 was that. In 2000 was that. Assume the growth is exponential. Let x be number of years since 1990. Okay. So what will the population be in 2050? So what I would do is yeah, so I do this. I do 782, 248 times b to the 10 power equals 894. Nine, 4, 3.
Why?
Because I got to figure out how it's growing in those 10 years. So I have to do the 10th root of that ratio. So I'm gonna use a calculator to do that.
And then you just stick that in the
Mhm.
in the thing, and you put 782 as the initial.
Right. And actually, I have a calculator here too. So by the way, I don't really have to do a 10th root. I could raise it to what power? Yeah, 1/10. You guys know, right? Yep. 894, 943 divided by 782, 248. And then raise that to the 0.1 power, which is 1/10. Okay. Which okay. So 1.0135. So it's about a 1.35% increase. Yeah, 1.35% increase per year. So in the year 2050, I'm kind of out of space here, so I'm going to use the space down below. Yeah. So y equals 782, 248 times 1.0135 raised to 60th power. So 782,248 times that number raised so we expect that many people in San Jose. 60 years after 1990 because year 2050
Oh, you can solve for it already.
for B.
Yeah.
Yeah, we did. Yeah, it's
Oh,
1.0135. We did. Okay. And when we reach 2 million people, well, then in this case, you set the equation equal to 2 million. And you solve for X. Yeah, you should be doing this log base of 1.0135. Yeah, I know we haven't talked about logs yet, but I know you guys learn logs, so I'm gonna do a log.
Why would you do, can you just do log like normally, like with base 10?
You can take a log of both sides, use log property,
Yeah,
but you gotta divide by 782,248 first.
yeah.
But yes, you can do that. You could take a ln of both sides, you could do that as well.
What does the topic is natural log?
Any bit base.
Wait, is the difference between natural log and log only just the fact that one of them accommodates for E?
No, base E. for
Base E
natural log.
for natural log.
Oh, okay.
Or continuously compounding.
Yeah, for E, yeah.
So we're getting a little ahead of ourselves here, but
Oh, yeah.
if I did alpha window, by the way, is how you can access change base for log. If I grab that, and if I do 2 million, 782,248, which I knew what it was anyway. Yeah, so about 70 years. Cool. We good? All right. I think, do I really want to do this problem here? Compounding interest. Let me look at the homework, see what's on deck. Okay, let's just do one more problem. We'll wrap it up. I'm going to jump to 69.75 years.
From 1990 or 2000?
1990. So the year 2060 roughly. Yeah, let's just do let's go in order. Let me not jump around. Let's do yeah, let's do this and wrap it up, okay? So we'll actually, you know what? I think you guys have enough to do the homework. Yeah, let's just stop there for today. We'll pick it up. We'll pick it up.